Hi everyone! Today we're going to be talking about geometric series and infinite series. Our objectives for today are that students will be able to find sums of geometric series, recognize the difference between convergent and divergent series, and use the convergent series formula. Let's get started. So just as a formal definition of a geometric series is the sum of a geometric sequence. Alright, just like series are always the sum of the sequences. To find the sum, we use a special formula. So the formula to find the sum of a geometric series is S sub n equals A sub 1 times 1 minus r to the nth power divided by 1 minus r. Alright, where n is the number of terms, and A sub 1 is always our first term, and r is the common ratio. Alright, so to find the sum of a geometric series, we say that S sub n equals the first term times 1 minus the common ratio to the nth power divided by 1 minus the common ratio. Alright, so number 1, we've got a geometric series here. As we can see, it's increasing by a common ratio. We're multiplying by 5 every time, and we've got addition symbols in between. That means we're adding all the terms together. Alright, so our common ratio, our r, equals 5 because we're multiplying everything by 5 to get to the next term. Our first term is 4. And our n is 14 because we're looking for the sum of the first 14 terms. So n equals 14. Now we're going to take these facts and plug them into our formula. So the sum of the first 14 terms equals our first term times 1 minus our common ratio to the nth power divided by 1 minus our common ratio. Now, plug this into your calculator. Let your calculator do all the hard work, alright? And this is why it's really important to have a scientific calculator here, because this is very difficult to do without it. Alright, we want to plug this into our calculator. Use parentheses around here. 4 times, parentheses, 1 minus, 5 to the 14th power, parentheses, divided by 1 minus 5, or negative 4. We get that the sum of the first 14 terms equals a very, very big number. 6,103,515,624. Alright, and this is why we're grateful for the formula and why we're grateful for scientific calculators. And that's our final answer. Alright, number 3. We've got a geometric series here. We're adding up our terms together. We know that our first term is 3. We know that our common ratio is 2 because we're multiplying by 2 to get the next term. Now, we do not know what our n is, alright? We don't know what n is, and we need to know what n is before we can use this formula. So, in order to find our n, we want to use our formula that we learned last lesson, alright? A sub n equals A sub 1 times r to the n minus 1 power. Alright, if we do this, we plug in our given information, we can solve for n. Alright, so we know that our last term, A sub n always stands for our last term, is 6,144. Alright, that's given to us, that our last term is 6,144. We know that our first term is 3. We know that our common ratio is 2. We don't know our n, and we say n minus 1. Now our goal is to get n by itself, so divide both sides by 3. We get 2,048 equals 2 to the n minus 1 power. Now the easiest way to solve this is, we're going back to what we learned about exponents, make them have common bases. So we can rewrite 2048 as 2 to the 11th power. And then we get 2 to the n minus 1 power. Now, oops, trying to shrink this down so I have some more room. Now that we've got common bases, set the exponents equal to each other. So 11 equals n minus 1. Add 1 to both sides, n equals 12. Now that was the missing piece of information that we needed. Now we can take this information, plug it into our formula. So the sum of this series, and we know it's the first 12 terms, equals our first term, which is 3, times 1 minus our common ratio of 2 to the 12th power. All right, and I don't know why I wrote that so big. Divided by 1 minus our common ratio, which is 2. Now we let our calculator do all the hard work. Have that scientific calculator. So we do 3, we put this in parentheses, 3 times, parenthesis, 1 minus 2 to the 12th power, parentheses, extra parenthesis around it, divided by parenthesis 1 minus 2, parenthesis. Plug that into our calculator and we get that the sum of the first 12 terms equals 12,285. And that's our final answer. All right, number 5. Number 5 looks a little different because it's written in summation notation. All right, and when we have a geometric series written in summation notation, it's actually much easier for us, all right, because it's still written in the form that we learned last time, all right? It's in the form a to the n equals the first term times r to the n minus 1, all right? We can see this right here is our r to the n minus 1, and there's an invisible 1 times this in front, so our first term is just 1, all right? Now, so we can easily identify that our r is 2. This is always our r. Our first term is 1. And another way we can find that first term is just by plugging in n equals 1. That's our first term. So when n equals 1, we get that the answer is 1. Because 2 to the 1 minus 1 equals 2 to the 0 power. Anything to the 0 power equals 1. All right, and then the other piece of information we need is our n. And in order to find our n, what we want to do is take 25 minus 1, right? Subtract them, add 1. 25 minus 1 gives us 24, plus 1 gives us 25. So n equals 25. Now we take this piece of information, these pieces of information, plug it into our formula. So we get the sum of the first 25 terms equals our first term, which is 1, times 1 minus our common ratio to the nth power divided by 1 minus our common ratio. Then we let our calculator do all the hard work, 2 to the 25th power. Nobody's got time to do that. Let your calculator do it. We get our final answer is 33,554,431. And we are very grateful for our calculators today. All right, number 7 is written in summation notation. Looks a little bit weird. Don't panic. We'll go through it together. All right, so number 7, first thing that we can identify, the number that's attached to the k minus 1 is always our common ratio, all right? So -3 is our r. Now, if we want to find our first term is when k equals 6. So in order to find our first term, we need to say when k equals 6. So -4 times -3 to the 6 minus 1 power. When we plug that into our calculator, all right, -4 times -3 to the 5th power, we're going to get 972. All right, so 972 is our first term. So we've got our first term and our common ratio. Now, our n, to find our n, right, we just do 20 minus 6, add 1. What's on top of the sigma minus what's on the bottom? 20 minus 6 gives you 14, plus 1 gives you 15. So n equals 15. take your given information or the information you just found, plug it in to this formula right here, and we can find the sum of our geometric series. So the sum of the first 15 terms, because we found out that n is 15, equals 972 times 1 minus, our common ratio is -3, our n is 15, so to the 15th power, divided by 1 minus -3. All right, and when you're plugging this into your calculator, be very careful with those parentheses. So start with one parentheses, then hit 972. Add another parentheses, 1 minus, parenthesis, -3, parenthesis, to the 15th power, parenthesis, double parenthesis, divided by, parenthesis, 1 minus, parenthesis, -3, parenthesis, then another parenthesis outside of that. All right, so this is part of the learning experience, is learning how to plug this into your calculator as well. Because if you plug it in wrong, you'll get the wrong answer. Your calculator doesn't always know how to do order of operations as it should. You have to tell it sometimes, and we tell it using the parentheses. So you plug that in using lots of parentheses, and we get a very big number. So the sum of the first 15 terms should be 3,486,784,644. Very big number. Thank you, calculators. All right, now we're going to be talking about infinite geometric series. And I think I had briefly mentioned it on the very first day when we did an introduction and an overview on everything. I had talked about infinite geometric series or infinite series before. And there's two types of infinite series. All right, the first type is when it looks like this, and we've got 1/2. All right, we've got a bigger number, and it gets smaller and smaller and smaller. All right, so when it's decreasing, and we've got a fraction, and we're cutting it in half, cutting it in half, cutting it in half. All right, what we can say is that the sum of this series, if we were to add up just the first term, 1/2 equals 1/2, all right? So the sum of the first term is just 0.5. Now, the sum of the first two terms, so S sub 2 means if we say 1/2 plus 1/4, we get 0.75. S sub 3 means the sum of the first three terms, so we say 1/2 plus 1/4 plus 1/8. That's going to give us 0.875. Then if we add up the first four terms, so 1/2 plus 1/4 plus 1/8 plus 1/16 gives us 0.9375. Then the sum of the first five terms, all right, because the next term would be what? 1/32, 1/32, all right, 1/32, all right, fraction, very small fraction. If we add all those together, we get 0.96875. All right, and if you see a pattern here, you see that it's getting infinitely closer to 1, but it's never gonna reach 1. So we say that a series that approaches a certain sum, we call this a convergent series, because we can say that the sum of this series, all right, the sum of this series is approaching 1, and that's what the arrow means. It means it's going to get as really, really, really close to 1, but it's never going to be 1. It's going to be lots of decimal places, infinitely close to 1, but never hit 1. This is a convergent series. Our series is converging to a value of 1. Now, our second example over here, we've got a value, and it's growing, we're multiplying by 2. It's getting bigger and bigger and bigger and bigger. If we were to say the sum of the first term, all right, the first term is just 0.5, all right, add the first term with itself, 0.5. Now if we say the first term plus the second term, the sum of the first two terms, we get 1.5. Now add the first three terms together. 1/2 plus 1 plus 2 gives us 3.5. Then the sum of the first four terms gives us 7.5. Sum of the first five terms gives us 15.5. Sum of the first six terms would give us 31.5. All right, and we can keep going on and on and on forever. All right, if you see a pattern here, you see that the sums are getting bigger and bigger and bigger and bigger, and it's going to get bigger forever. So we say that the sum of this series is approaching infinity because it goes on forever and it gets bigger forever. And we call this a divergent series, a series that does not have a certain sum. It just gets bigger and bigger forever and ever. All right? And there's a way that we can tell whether a series is convergent or divergent. And how we can do that is we can look at the common ratio. So if the absolute, if the absolute value of the common ratio is less than 1, then we know that the series is convergent. All right, and we know it's going to converge to a certain value or a certain sum. If the absolute value of the common ratio is greater than 1, then the series is divergent. And that means it doesn't have a certain sum. It's going to get bigger and bigger forever. We're going to use this to help us determine if it's convergent or divergent. Now, if an infinite geometric series is divergent, there's nothing we can do. We just classify it as a divergent series. But if the absolute value of our common ratio is less than 1 and it's a convergent series, there's a formula that we can use to find the sum of a convergent infinite geometric series. And that formula is S sub n equals the first term times 1 over 1 minus the common ratio. All right? And this formula will help us find the sum of that convergent infinite geometric series. So what is that value, that certain sum that the series is approaching? All right, so number 9, the first thing we want to do is determine if it's convergent or divergent. If it's divergent, nothing we can do. Classify it as divergent. If it's convergent, then we can use our convergent series formula to help us find that sum that it's approaching. Okay, so first of all, let's look for our common ratio. We see that it's going down, down, down. We're dividing by 4 here every time. All right, dividing by 4 is the same thing as multiplying by 1/4. All right, so we know that we're dividing by 4 every time. Dividing by 4 over 1 is the same thing as multiplying by 1/4. So this is our common ratio. R equals 1/4. Now, if R equals 1/4, we take the absolute value of 1/4, which is 1/4, and that is less than 1. Therefore, because the absolute value of our common ratio is less than 1, this is a convergent geometric series. Now, because it's convergent, we can use our formula to help us find the sum that it's approaching. So, our formula is S sub n equals our first term times 1 minus r. So all we need is our first term and our ratio, our common ratio. R is 1/4, first term is 1. Plug it in. So we get 1 times 1 minus 1/4, which gives us 1 times 1 over 3/4, which gives us 4/3. All right, so the sum of our infinite convergent geometric series is 4/3, and we're done. All right, number 11. First thing we want to do is find R. So can't really identify R right off the top of our heads by looking at this because we've got so many decimals. So the easiest thing to do is take the second term divided by the first term. So R equals 3.48 divided by 5.8. Plug that into our calculators and we get R equals 0.6. Now the absolute value of R, absolute value of 0.6 equals 0.6, and this is less than 1. Therefore, it is convergent. All All right, now because it's convergent, we can use our formula to help us find the sum. Our formula, S sub n equals first term times 1 minus 1 minus r. Our first term is 5.8 and our r is 0.6. Plug them in. 5.8 times 1 minus 0.6. Plug that into your calculator, let your calculator do all the hard work, and we get 14.5. And that's our final answer. All right, number 13. We like this one, all right? It's definitely an infinite geometric series because the number on top of our sigma is an infinity symbol. That means it goes on forever. We start with x equals 1 and we go on forever. We can easily identify our r because it's the value attached to the x minus 1, all right? So r equals 1/4. The absolute value of 1/4 is 1/4, and 1/4 is, right? Absolute value of 1/4 equals 1/4. That is less than 1. Therefore, it is convergent. Use our formula. S sub n equals first term times 1 minus our common ratio. All right? Or 1 divided by 1 minus our common ratio. First term. Now, in order to find our first term, here's where it's a little tricky. We gotta plug in x equals 1 into our formula in order to find our first term. So our first term is when x equals 1. So we say negative 2 times 1/4 1 minus 1. Now, we get negative 2 times 1/4. 1 minus 1 gives us 0. Anything to the 0 power equals 1. So we get negative 2 times 1. Our first term is negative 2. Then we say 1 divided by 1 minus our common ratio, which is 1/4. Negative 2 times 1/3/4. Same thing as negative 2 times 4/3. And we get that the sum is negative 8/3. And that's our final answer. All right, last but not least, we've got a geometric series written in summation notation. It's infinite because the number or symbol above the sigma is an infinity symbol, goes on forever. First thing we need to do is identify our common ratio. And we can easily identify our common ratio because it's whatever's attached to the w minus 1. So r equals negative 5/2. Common ratio is negative 5/2. Now we want to take the absolute value of negative 5/2. Absolute value of negative 5/2 is just 5/2. And 5/2 is the same thing as 2.5, right? Now 2.5 is greater than 1. Therefore, this is a divergent infinite geometric series. All right, and there's nothing more we can do. We just say that our r equals negative 5/2, and this is a divergent series. And we're done, all right? We can't find the sum because a divergent series goes on forever. It gets bigger and bigger and bigger forever. All right, and that wraps up our lesson on geometric series and infinite geometric series. I hope you learned a thing or two about them today. And if you have any questions, please raise your hand. Call me over so I can help you. Otherwise, look to the board to see what to do next. And I hope that you have a great day.